This talk will describe our novel iterative filter adaptive network for single image defocus deblurring. Defocus deblurring is to restore an all-in-focus image from an image containing defocus blur. It is highly demanded by ordinary camera users and can facilitate higher level vision tasks such as semantic segmentation and object detection. Despite the usefulness, defocus deblurring remains a challenging problem as defocus blur is spatially varying in size and its shape also varies across the image. A conventional strategy is to estimate defocus map containing per pixel blur size and to perform non-blind deconvolution. However, it often fails due to the restrictive blur model, which disregards the nonlinearity of a real-world blur and constrains defocus blur in specific shapes such as disk or Gaussian kernels. Recently, the first end-to-end deep learning-based method, DPDNet, has been proposed. DPDNet outperforms previous approaches for real-world defocused images as it is trained to directly restore a sharp image. They showed that dual-pixel data can significantly boost the deblurring performance and presented a dual-pixel defocused deblurring dataset. However, the results often contain ringing artifacts and remaining blur, mainly due to the naive unit architecture, which is not flexible to deal with spatially varying and large blur. To resolve such problems in this paper, we propose an end-to-end network embedded with the novel iterative filter adaptive network named IFAN. To handle the spatially varying nature of defocus blur, IFAN does not directly predict pixel values, but generates spatially adaptive per-pixel deblurring filters. To efficiently handle large defocus blur that requires large receptive fields, IFAN predicts stacks of small-sized separable filters. To apply the predicted separable filters to features, we also propose a novel iterative adaptive convolution layer named IAC layer that iteratively applies the filters to defocus the features. By iteratively applying the filters, the IAC layer removes possible errors may be caused by using separable filters. And thanks to one-dimensional filters, the IAC layer secures large receptive fields at low memory and computational cost. To further improve the single image deblurring quality, we train IFAN to estimate defocus disparity by exploiting dual pixel data, whose disparities are proportional to defocus blur magnitudes. With the disparity map estimation task, IFAN is trained to predict more accurate deblurring filters. Moreover, we introduced the reblurring network to utilize deblurring filters predicted by IFAN for reblurring all-in-focus images. With the reblurring network, IFAN is trained to predict deblurring filters containing valid information about blur shapes and sizes, which eventually improve the final defocus deblurring quality. We use dual-pixel images from the DPDD dataset to train our network. Note that dual-pixel images are used only during training for disparity map estimation and reblurring tasks. Here are the experimental results of the ablation study. We showed that advantage of explicit filter prediction in flexible handling of spatially varying and large defocus blur. Moreover, explicit utilization of filters has more potential in observing extra defocus blur specific supervision provided by dual-pixel images. The model with the disparity map estimator is better in recovering texture, while the model with the reblurring network is better in restoring image contents. Our final model with all components achieves the best performance in every measure. Our model outperforms previous approaches by a significant gap with a smaller computational cost. Moreover, although our model uses a single defocused image, it outperforms DPDNet taking dual-pixel images. Qualitatively, compared to the previous ones, our method better handles spatially varying defocus blur, large blur, and better in restoring image structures as well as textures. To quantitatively measure generalization ability of our method, we prepare a new dataset named RealDOF. To capture image pairs of the same scene, we built a dual camera system with a beam splitter. The table shows that our model clearly improves the image quality, showing that the model can generalize well to images from other cameras. Qualitatively, while the results of DPDNet contain some amount of remaining blur, ours looks much sharper. We also qualitatively compare methods on PixelDB testset and CUHK blur detection dataset. The results show that our method removes defocus blur and restores fine details more successfully than DPDNet. The proposed network is still limited in handling significantly large defocus blur. Also, our network may fail for blur with irregular shape or strong highlights. We are planning to extend our RealDOF testset by adding more image pairs of diverse blur types captured with various cameras and lenses. Thank you for listening. For more information including code and dataset, please visit our website.